thanks for Michel for the invitation and also for the hospitality online. I mean, absolutely. I mean, I'm very happy to give such a talk. I mean, I think during the past 5 years, I switched more time. I mean, spend more time on the muon physics, especially muonium physics and some muon detections in multi-discipline applications. This is why I call it muon detection across the road. So, well, this is the laboratory, I mean, I built from the scratch in Sun Yat-sen University. On the right-hand side is the logo for our recently proposed experiment, Muonium to Antimuonium Conversion Experiment, abbreviated as MACE. Conceptual design report of such an experiment was released at the end of last year. It will soon be published in a journal. So first, I will just give a brief introduction on the high-energy physics group in our university. So we are located like basically in the nearby 3 cities. So we have various School of Physics and School of Physics and Astronomy, SINO, French Institute of Nuclear Engineering and Technology. And very recently, they even established a new School of Science in the Shenzhen campus. And as clearly you will see that we have like more than 30 faculty members working on high-energy physics, nuclear physics, including theory, phenomenology, experimental physics. And all the topics are listed here, including muons, neutrinos, neutrons, and even collider physics, astroparticle physics, and even the radiation shielding materials. So we are still hiring new faculty members as well. So if you have young postdoctor or PhD student who are searching for jobs, please feel free to contact me. And these are the university locations. Sorry, these are Chinese. I mean, this is the central campus, but basically it's my campus, South Campus in Guangzhou. And this is Zhuhai campus here. And this is Shenzhen campus here. Sorry. In the nearby, there are so many big scientific facilities around. So here is a Juno, German underground neutrino observatory. I mean, it's more than 2 billion Chinese yuan investment from central government. And here there is a China spallation neutron source. Well, the phase 1 was already the accelerator is running. Well, the phase 2 is also approved very recently. 3 billion Chinese yuan will be invested on the upgrade from 100 kilowatt towards 500 kilowatts. 1.6 GeV proton driver for the neutron spallation neutron source. And the nearby city, Huizhou, there is another 2 accelerators. One is the heavy ion accelerator facility, and the other one is the China Initiative Accelerator-Driven Supercritical System. And those 2 were invested by like more than 6 billion Chinese yuan from the central government. It's under construction. Half is going to take data at the end of this year. CADS is under construction. So I would say our Bay Area is completely surrounded by domestic accelerator facilities. I mean, obviously, as soon as we have a very powerful proton driver or heavy ion accelerator around, it's golden chance to propose some secondary beam science and technology. For example, muon beam science and technology. Maybe we have a good chance as a local university. Our university just finished the 100th anniversary, so it's 100 years old here. And this is my team. So all the work I presented here, I have to appreciate all the bachelors, masters, and PhD students, and even some electronics engineer who are working with me. So this is the team. It's I would say in the past decade, I have been building such a nice team, and I'm very proud of this team. So now we are going to the real physics part. So first, I will motivate you a little bit on muon physics, since we already have an expert, and probably we have more experts from Sydney, like Michel Schmidt. He already worked a lot on the muon physics and helped lepton flavor violation stuff. I mean, as everybody is familiar with the symmetries of standard model, I mean, it's SU3 crossed by SU2, S crossed by SU1, and the quantum chromodynamics plus electroweak unification were done very well. But since there is an absence of the right-handed neutrino, this can lead to the lepton flavor symmetry, like baryon number conservation and lepton flavor conservation. By the way, in the particle data group, recently somehow authors changed the name from lepton flavor to the lepton family number. So now we say it's lepton family number conservation. So in standard model, lepton flavor is always conserved. However, we have found, or we have discovered the neutrino oscillation. So the neutral leptons oscillate. And due to the discovery of the neutrino oscillation, Art McDonald and Kajita-san won the Nobel Prize in 2015 for this, for the nice fact that neutrinos should have mass. I would call it, this is the first experimental evidence, direct evidence beyond the standard model to show that neutrino must have mass. And on the right-hand side, this all the global picture of the neutrino mixing, like the diabase neutrino experiment, Reno and double Hue experiment measured the theta-1,3 very well, and the super K, and together with other atmospheric neutrino experiments, measured the theta-2,3 very well. And the solar neutrino like SNO and others measured the theta-1,2 very well. And there are also two mass squared difference were well measured. Of course, there are still more questions to be answered, like whether there is CP violation in the leptonic sector and how is the mass hierarchy, as we didn't identify or determine the mass ordering in the atmospheric neutrino experiment. And the next generation reactor neutrino experiment, Juno, will definitely do something on this in this direction. I'm also one of the members in this direction. But today, I'm not talking about the neutron leptons. I would like to tell you more about the charged leptons, especially its flavor violation processes. So since neutrino oscillate and neutrinos must have mass and mixing, so in principle, if you extend the standard model a little bit with massive neutrinos, there should be charged lepton flavor violation. But if you just use the tiny neutrino mass terms and plug it in and derive the mu2e gamma processes, you will immediately realize that branch ratio is extremely small. It's like 10 to the minus 53 compared to the mu2 3 lepton decays. So this might be hopeless. But again, some more physics models, especially like our host, Michel, is also one of the excellent model builders. They build also several flavor models. They might predict the observable charged lepton flavor violation processes. Well, very recently, his collaborators like Lorenzo and Claudia and Michel, they wrote just a paper, submitted, I think, 2 months ago to clarify the charged lepton flavor violation processes in different units. So for one unit processes, including like mu2e gamma experiment, MEGA2, like they are going to measure the mu plus decay to E plus gamma, and the mu2 process, mu plus decay to E plus, E minus, and E plus, and both are hosted in PSI, Switzerland. And in Fermilab, there is a mu2e, and in Japan, in JPAC, there is a COMET experiment. Both are searching for mu-E conversion processes, heating the high intensity mu minus towards the aluminum target, and to check whether there is a simultaneous conversion to electron in such a process. Well, there is one process which was there for a long time, but the experimental results was just was finished in 1999, and there was no more result since then. It's Muonium to Antimuonium Conversion Experiment, and that's why, well, since in our local area, those accelerator centers are just online, are just around the corner. Maybe it's a time to propose something new towards the Muon charged lepton flavor violation processes. And as soon as we found some charged lepton flavor violation processes, it's a clear evidence of the new physics. So it will also provide a strong constraint to the new physics models. So, I will just have a quick overview of the global picture. So on the right-hand side, there is also an effective field theory description of such a charged lepton flavor violation process on the Wilson coefficient combination and the high energy scale where the new physics lives. So this, you can clearly see that like mu2e gamma, mu2 mu-E conversion, they are quite complementary with each other. And all those processes were now under the searches by different experiments. Well, of course, we can always also trace the way, like very recently, the Muon G-2 in Fermilab announced their new results. So doing the precision measurement of the muon properties, like muon anomalous magnetic moment measurement, could also tell us more whether there is any new physics beyond the standard model. As soon as you found something which is different from the theoretical prediction, then there might be a chance. So in the history, there is also like muon lifetime measurement, muon capture coupling constant, electroweak interaction, and muon polarization measurement. Like at at TRIUMPH, there is also a muon decay Michel parameters measurement. In JPEG, there is also a group who are working on the muonium hyperfine structure. It's basically a nuclear physics-driven experiment to check the hyperfine structure from the muonium. So we could say the low energy CFV experiments complement high energy frontiers, since you can check the EFT's high energy physics scales. So it's even much higher than the LHC 14 TeV. And also Tong Li and Michel also, wrote a paper to argue that there is also a like collider physics who are very sensitive on this direction, like CPPC, FCCEE, ILC, or CLIC. Well, if we put this low energy CFV experiment result into the same picture or under the same assumption, you can clearly see that they can also be complement with each other. And also clearly you already saw that. So several neutrino mass generation models could also offer CFV process. So it could also constrain the neutrino physics as well. They share the same Yukawa coupling, no matter it's in standard model or in some models beyond standard model. So these are the detector design for the comet. It's an S shape, and this is for mu2e in Fermilab. It's also very similar, like a snake. And on the right top, you could see that in history, actually people start not with the accelerator beam. People really recognized the muon physics and the importance of muon physics early days without even accelerators. They're using the cosmic ray muons. So because it's free and it's everywhere around the world. And here there is mu2e gamma, mu2e, mu-e conversion. And one channel I can show you like this purple diamond muonium to antimuonium conversion experiment. It was stopped here in 1999, published by PSI. Basically, I think a few years ago, I contacted Klaus Jungermann, who used to be the spokesperson for MACE experiment, and contacted him. I said, I'm very interested in this channel. And he was very active and also even sent me some German theses to ask me to digest it first. So I would very appreciate his, enthusiasm and also his suggestions and comments. Nowadays, excuse me. Nowadays, we are at this corner. Clearly, you will see that people are still chasing like mu2e gamma, mu2e, mu-e conversion, while muonium to antimuonium conversion is way behind. So that's why, since in China, we are just proposing some high-intensity muon beamlines, maybe it's a chance to propose some muon science experiments. That's why I proposed MACE. At the very beginning, it was a very rough idea. I can show you later, but later it was well welcomed by the local community and also international communities. And this is the very nice and fancy design for the MEGA2 experiment, including all different tracker, magnetic spectrometer, and a clarometer. And this is the mu23e. They even developed this very advanced silicon-based tracker together with the scintillator tiles and some target design to improve the previous world-leading experiment result. So anyhow, muonium, it's such a leptonic hadronic or hydrogen isotype. It's like change the hydrogen proton into the mu plus. It forms the found state. And we just check whether this mu plus E minus can convert to antimuonium, like mu minus E plus simultaneously. And this is definitely a unit 2 violation for CLV processes. So some people may argue that, well, since we can't even find or discover the unit 1 violation process, why should you care about the violation of Unit 2. I said, well, this is complementary with each other. Since you don't know the underlying theoretical models, then everyone or every model has the chance. And of course, we can also follow the previous ways like Ander Govella did, form the Wilson coefficient in the horizontal axis and the new physics scale in the vertical axis, and make it a comparison with some like Tristan, the collision process, and also even LHC to make a comparison how we can improve the new physics sensitivities. So if we can reach our MACE goal, like goes to the conversion probability limit up to like 10 to minus 14 or 10 to minus 10 to minus 13, we can like already be very sensitive to a few tens or even hundreds TeV energy scale. So this is very, very promising. And also it tells us that it deserves our effort. And this is the old result in this shaded region. This was done in 1999. So if we can improve them more than 2 orders of magnitude or 3 orders of magnitude, we can definitely compete with the collider or scattering experiments. Well, thanks to the EFT, effective field theory framework. So in the worldwide, there are some various accelerator muon sources. So including like in Europe, there are a lot. Like in UK, there is ICES for muSR, is mostly for applications. And in PSI, there is also various scientific experiments or muon science experiments like muon-EDM, MEGA2, mu3E, and MUSE and QUIMERA, and so on. And in United States, there is like muon G-2 in Fermilab that just finished. And next phase, they will go to mu2E experiment. And in time, there were also like Muonium studies. Like in the old days, there is TWIST. So in Japan, there is JEPAC. They have proton driver. They also offer the secondary muon beam. So they propose like muon G-2 experiment, muon-EDM experiment, COMET experiment. I'm one of the members there. And also Muonium hyperfast structure experiment. So in China, there are various accelerators. Even in our area, there are like HAF, CIADS, CSNS. In Shanghai, there is a SHINE, is for light source, electron beam. There is also a group led by Kim Shang, who is also proposing like muon beam based on right before they are beam dumps, because they use the accelerated electron beam to generate light for light science and application. Well, meanwhile, there is a strong power that can be used for some secondary beam, but the original design was not included. So they proposed something right before the beam dump for the muon production and so on. They can use for muSR and for muon tomography or muon science. So anyhow, as I mentioned, for fundamental physics, I would list all these CFV processes here. So MEGA2 is data taking, mu2E is under construction, COMET is under construction, mu3E is under commissioning. I think it's taking data very soon. And for the Muonium to Antimuonium conversion, it was stopped in 1999. Since then, no more experiments were proposed. So very recently, we tried our best to work on this direction. And why is it this? One of the motivation, at least, well, since we don't have the muon beam yet, why not propose something new? We have more time. Another thing is like, after more than 2 decades, we should have more enhanced muon beam intensity and advances in the detector technology. We could do something better, design a new experiment, and then to make a breakthrough. And this is a global picture. So if you put the schedule here, I would just say that we just announced the CDR. Now we're working very hard on the technical design report. In the meantime, we can also split it into 2 phases, because the beam will not, especially the high intensity beam, will not come in a day. Rome cannot be built in a day. So we wish that we can build our detector prototype together with the beamline step by step in different stages and so on, and hope that in the next decade we can reach our design goal, like more than 2 orders of magnitude improvement. Okay, I hope that I motivated you. The muon physics is very important, especially MACE is also a good experiment, because CFV selects neutrino mass generation mechanisms, like there is type 1, type 2, type 3 SYSU mechanisms for various neutrino mass models, but which one is the correct one? For the muonium to antimuonium conversion experiment, double-charged Higgs can propagate such a muonium to antimuonium conversion processes. And also the charged leptons and neutrinos share the Yukawa coupling. So we would say the CFV complementing neutrino physics. This lepton, charged lepton flavor violation process is definitely also complementary to the quark flavor physics, because I mean there are also different generations. And also the low energy CFV experiments could be very sensitive to the high energy scale new physics states, and it is complementary to a high energy frontier like the LHC physics, Collider physics. So muonium conversion experiments have started for decades. Both we have the opportunities and also the challenges, since I mean there must be a reason behind why people stop in this direction, because it's tough. I will show you later. And also in the Chinese initiative accelerator facility, all these big facilities is dreaming to build high intensity muon source, and we could propose something new beyond the current generation muon physics experiment. So that's why we propose this MACE experiment. And the history was like this. So in the SNOWMAS 2021, I gently submitted a letter of intent. I mean, eventually it was translated in the final paper with my colleagues or collaborators to probe the double charged Higgs boson with muonium to antimuonium conversion experiment. So, and then later there was a theorist, Alexei Petrov, who used to be a professor in Wayne State University. Now he is in University of South Carolina, and he is very interested in the theoretical part. So he wrote a letter of intent to the SNOWMAS in theory. So I wrote it in experiment part. And then the convener asked us to combine together and then to submit a kind of white paper. And this was done 1 year after that. And in various conferences, Bertrand from Caltech even cite us and also tell us that, yeah, this is important, please keep moving. And so we were very happy. And even in some conference, he even cited my old, very preliminary Chinese slides. I'm not sure whether he understood what I wrote there. And 2 years ago, and there was a workshop in Fermilab on the future muon physics program. They also invited us to give a talk, but it was early in the morning. So I sent my bachelor student, who is also dominating the R&D for the MACE experiment, to give such a talk online. And the proceeding was submitted to archive in September of 2023. Well, somehow I was also invited for the International Advisory Committee at the New Fact. This year, New Fact will be held in Liverpool University in United States, in UK. So they still welcome new abstracts and new participations. Please feel free to submit your abstracts or attend the conference. And we also gave the plenary talk in the CFV 2023 in Heidelberg University. So basically, our goal is to improve the previous or the world-leading result by more than 2 orders of magnitude. Well, here I projected the sensitivity, like a single event sensitivity towards the data taken days. Basically, in 1 year, we wish we can reach such a goal. And clearly, there are physics behind the whole story. And there are also the accelerator and the detection technology advancement. So we expect to at the forefront of the global research in the muon physics if the MACE experiment is being built. So, I mean, we finished the conceptual design last summer, and we invited several experts domestically and also some international colleagues to join the conceptual design report review. And in our campus, actually, we held a workshop, and this is the indical. And then after that, we received several comments, and we basically revised our conceptual design report based on the comments and the suggestions. Then we submitted last October the conceptual design report. And at the beginning of this year, we submitted to the journal Nuclear Science and Techniques. It's under minor revision. I think it's not with editor. It should be published somewhere. So now I'm going to introduce more about the conceptual design of such an experiment. So since I told you that it's a chance and it's also challenges for the MACE experiment. Why? Because if we want to improve such a sensitivity, improve the limit, we should have something improved. So I listed the major milestones or key steps we should work hard on. One is to increase the muonium production efficiency in vacuum, because most of the mu plus hitting the target, they can generate muonium, but most of them are absorbed by the materials, because the muonium lifetime is also very similar to the muon lifetime. It's like 2.2 microsecond. And second part is to design a high-resolution magnetic spectrometer to advance the detection technology to make the better electron-positron identification, so that we can reconstruct the signal or noise or suppress the noise, or we call it the increase the signal over noise ratio. And for the muonium production, well, we tried, as Klaus Jungermann, the previous pioneers, sent us some German version thesis. We tried to reproduce the muonium production with our simulation tools in the silica aerogel, in the silica powder first, and then we swiftly moved to the silica aerogel, because in JPAC there was a crew who is working on the Muon G-2 experiment in JPAC. They also proposed the muonium high efficiency methodology. They used the later perforated silica aerogel to generate the muonium in vacuum, and they did it very well and with very nice target material and very nice beam data results. Well, we did the simulation, and then we realized there was some data in the community, and then we tried to reproduce the result, and it was very well reproduced with our simulation tools. And this is Sihan's work, and he finished his bachelor thesis mostly in this direction, and also got a very nice result from the university. And this work was eventually published at the beginning of last year in the Physical Review D. It was highly technical, but it was very useful, and also we received very good comments of our collaboration invitation from Mipsan in the JPAC Muon G-2 spokesperson. And eventually there was also a PhD student who used to work in the KEK. He also proposed a multi-layer silica aerogel to generate the muonium in vacuum. Well, of course, they proposed this for the Muon G-2 experiment, but it is also useful for our muonium to antimuonium conversion experiment. And we basically follow the same idea and plug it into our simulation tools. And we eventually realized, yes, we can improve 2 orders of magnitude in the vacuum muonium source intensity. So this is the major conclusion. Well, but of course, this is the conceptual design. We still have to do more prototype tests. So recently, we are still fabricate the silica aerogel in our domestic laboratory, and then try to lower the the intensity, the density of such a silica aerogel, and also do the beam tests. We will do the beam tests probably very late this year or at the beginning of next year, either in JPAC or in PSI. So how to identify the signal on the background? Why it is so challenging? Because we can develop such a detector system to identify the faster electron and the positron and slow positron to identify the muonium converted to antimuonium. This is their decay product. Okay, so we basically didn't recognize mu plus E minus directly. We recognize the mu plus E minus decay product is like either faster electron, slow positron, or faster positron, slow electron, to identify whether it's muonium or it's antimuonium. If this is a signal, it means that it's already from the antimuonium. We just do the coincident measurement. But nevertheless, in standard model, there are even intrinsic background. There is mu plus 5-body decay, which can generate E plus E minus pairs to hinder us. So this is the case. And the branch ratio is tiny. It's like 2 point something times 10 to minus 5 for the branch ratio. But as I said, we are doing the high intensity muon physics. So even though the branch ratio is 10 to minus 5, but if you multiply it by the 10 to the 8th mu plus per second, it will definitely dominate such detection processes. So we were very worried about this intrinsic background at the very beginning. And the second thing is like the muonium decay products could also hit the detector wall, basically, the magnetic spectrometer wall, and then get this kind of scattering process, and then to fool the faster electron and slow positron. And this E plus could come from the mu plus decay, by the way, the unabsorbed mu plus beam in the muonium target. And the third background could come from the MACE reconstruction and even cosmic ray, since cosmic ray muons come every day, everywhere. And they could also form the coincident or accidental background, since we are doing the coincident measurement. So we also think that we should trace the faster electron and the slow positron at the same place, at the same position, to improve our signal over noise ratio. So, for example, we can propose the method to do the vertex reconstruction by select the electron-positron tracks. So we can use the electromagnetic field, basically we call the magnetic field spectrometer, to do such a tracking processes. And also, for so many accidental background from like cosmic rays or MACE reconstructions, we prefer have the pulsed muon beam, so we have timing structure to control such a background. And also, we want to do the timing coincident. As I said, this electron and the positron, if the positron come from the shell, is a forming hydrogen-like atom, the bond state for such an atom is like 13.5 electron volt. It's extremely low energy, so it's hard to detect. Therefore, we prefer to use the time of flight to trace it back. So we want to transport it to the far end and then do the identification and so on. So eventually we wish that we can have both excellent timing resolution and excellent vertex resolution with the pulsed muon beamline to reach our goals. And for these purposes, we designed such a MACE detection system. It includes the electromagnetic spectrometer and the positron transportation system, like this S shape, and the electromagnetic calorimeter. So some of your colleagues might smile at it. Well, this looks like a collider experiment. Well, you're right. It's like a fixed target experiment for high intensity frontier. So here I gently introduce how it works. So if we use the high intensity positron, mu plus beam to hit the muonium target, like silica aerogel with multiple holes, and then it generates muonium. Okay, as soon as it converted to the antimuonium, we can see their decay product, like Michel electron, and transported positron towards the far end with the MCP to detect the position, and with the EM calorimeter to detect the back-to-back two gammas to reconstruct their time and also to reconstruct their energy. So we call this is the triple coincident with magnetic spectrometer to reconstruct the Michel's electron and an MCP plus electromagnetic calorimeter to reconstruct the atomic positron. So it's an extremely difficult task, but at least we have a very good and a baseline design. Later, we plugged all these things in the simulation tool. And we also built the simulation tools from the scratch based on Gen 4 and finished such a task. And then eventually we optimize all these different parts, and we realized how the multi-layer design should look like and how the timing tile, the TTC, basically it's the tile, tiled timing counter is made from the scintillator detector, and the CTC is the central drift chamber, and so on. So this is how the gas mixture looks like, and how the timing we need the timing resolution from the TTC, and also how the positron transportation system looks like, and which basically high voltage we should use is a linear accelerator to transport such a positron, and also how large and how the shape of the electromagnetic calorimeter looks like, and what the energy resolution looks like, and the detection efficiency. And also for the microchannel plate, we also specify our requirements. All these things were fully optimized and basically by the mass scale Monte Carlo simulation to reach the physics goals. And these are the Toyo Monte Carlo simulation for the muonium conversion signals. Here, I showed. I'm not showing the muonium to antimuonium conversion. I'm just showing you the muonium decay products result and whether we can reconstruct them. And this is the targeted region. This is the MCP region. After the positron transportation system towards the far end, and then we trace it back to the same place and same position, and then eventually project it to the distance of the closest area and the time of flight, trace it back to the same timing position. And we clearly see that we can reconstruct the muonium very well, and then swap the magnetic field. We can trace or we can track whether it's antimuonium. And for the five body decay products, we also check whether it could dominate the background. And as I showed you in the left corner, bottom left corner, we can clearly see that their five body decay electron spectrum is a kind of going down slowly while the signal is going up, and then we can have a good cut and to separate this background. Basically, in our original wish list for the 10 to the 8 mu plus per second running in a year, we can have the background level like less than 1. So we can still reach the background free if we have such a very optimal beam and also very optimal detection system. So we were very happy that we can suppress the five body decay products. You may even wonder, what about the next leading order five body decay? I also checked. It's a very fortunate thing that it's not an enhancement. It's even a smaller contribution. Basically, it's a minus sign for the next leading order theoretical calculation. I did check that. PSI people had a very nice tool. It's called MacMuller for such a next leading order rare decay processes, because they are used for the mu2 and the mu2 gamma simulations as well. So this is the student developed Sihan Zhao. He is a PhD student now. Well, he originally was a bachelor student. Now he's a PhD student. He developed such a framework based on Gen 4. So we have all the simulation, reconstruction analysis, and event display, and all the library, external libraries, and these are detector descriptions, and for our further simulations. On the right bottom part, you can see the tracing. Basically, it's a display, and we just use the game engine, okay, 3D game engine to show how the detector looks like, and how the event looks like, and how the heat or the track looks like. Very soon we will announce a video for this process. So we wrapped up everything, like the detector design and also the beam information from our accelerator colleagues, and then plug them in. And also all these detection efficiency and even the geometric acceptance and so on inside. And we calculate the single event sensitivity for such a rare process. We are very confident if we can build such a detection system, we can reach 1.3 times 10 to minus 13, such a high sensitivity compared to the 10 to the minus, it's 8 times 10 to the minus 11 in the old days, 1999. And also I told you, well, muon beam lengths for 10 to the minus 8 mu plus per second will not come in a day. They might come step by step. So we also would like to develop like staging scenarios. So more simulations and also data analysis should be validated with prototypes, since all these are based on Monte Carlo. Well, should we be very confident, or we should do the more prototype tests with such a simulation tools? So this is the plan and our timeline. So first stage, we're not going to the muonium to antimuonium conversion. We're going to like muonium production and muonium rare decay process, or muon rare decay processes. If the surface beam come in like 10 to 6 or 10 to the 7, and we control the momentum spread and also the beam spot size at this level. And for the final physics goal for muonium to antimuonium conversion, like MACE, we reach 10 to the 8th mu plus on target per second. And we prefer the pulsed high repetition rate, like 20 to 50 kilohertz. And also the momentum spread is also well under control, and the beam size is well under control. We basically send all these requests and the requirements to our accelerator colleagues. It's under design, so it's a good thing, we just send our requests or specification at very earlier days and let them think about it, work hard on that. And for the phase 1, this is now the detector design looks like. And we were mostly interested in these two processes. One is the muonium decay to 2 gamma processes. The latest result was 1959, 10 to the minus 5. And also the second one is mu plus decay to E plus and 2 gamma process. The latest result was 1988. Well, there were also some new physics like dark matter physics or dark matter particle or action-like particles. Like Michel also worked with Lorenzo Calipi on this direction, basically involved in CLV processes. And also there are also some other processes to be probed in JPEG or in some other areas, or even in PSI, like pi rare decays to search for CFV process as well. Anyway, there are key challenges. No magnetic field. The detector is exposed to the overwhelming background. So we need to think about how to use the high-intensity muon beam, have more statistics, and we should develop a faster response detector to mitigate the pile-up events. And we should think about the sci-fi scintillating fiber tracker plus the tiled timing counter. These are all scintillators for precise timing, position, and electron gamma discrimination. We wish to build such an electromagnetic calorimeter to have the high granularity and large acceptance and high energy resolution. For these purposes, and students already implement those rare decay processes in the simulation package, and to trace the collimated back-to-back 53 MeV gamma, and to see the signal looks like this. These are the pair-up events, and this is the theoretical calculations as well. Well, there are also dominant backgrounds, like the similar topological pile-up events. So we should increase the simulation efficiency because, the backgrounds are very are dominating. So we use the important sampling method. We also optimize the selection requirements. For example, for observables, like the track angles, the energy difference, the reconstructed energy difference for the 2 gammas, and also the total energy as well, to scan to reach the best cut for the significance, so that we can acceptance. The geometric acceptance is at this level, the reconstruction efficiency at this level, signal efficiency is about half, and the background suppression efficiency is like this. So the overlap between signal and background in the spectrum is dominated by the energy spread and the tail in the electromagnetic calorimeter. There are also systematic uncertainties in calibration and reconstructions to be quantified. And this is the sci-fi tracker designed by one of the students and also our colleagues. And the bottom left part is show you how the EFT calculation offers the new physics sensitivity. And this basically, we can use the simulation results to quantify the signal efficiency and the spatial resolution and the timing resolution. And we can build the prototype to check it. We have a small prototype, by the way, about the geometry. And for the tiled timing counter, we also do the serious optimization. It was done by one of my students. And then we need so many different plastic scintillator detector and do the timing information, offer the timing information for the tracker. And for the MACE phase 2, the positron transport system, basically it's a LINAC design, and it was done by one of my bachelor students as well. And basically it's how to make such a curved transportation system and to compensate the electromagnetic field from different range to the far end electromagnetic spectrometer. it is not an easy task. It's non-trivial. So these are all the EM field distribution, how it looks like. And again, he's building up such a prototype in our laboratory as well. And these are the temperature distribution of such a validated, validation prototypes. So this is how the electromagnetic coils look like. And then the design of calorimeter, it was done by the PhD student Si Yuan, and this is the energy resolution and the signal efficiency requirement. And also he built the prototype and sent it to the, sorry, I didn't show the prototypes here. I mean, it was in the CDR as well, and it was published in a single paper very recently. And for the MCP plus ECAL prototype tests, well, MCP, because in China, due to the German Underground Neutrino Observatory, Juno experiment, there is a group in IHAP to develop the MCP PMT, and they are very good at MCP as well. So one of the students, Hua Xinpeng, and also his supervisor, Shulin Liu, they are working together with MCP. So they also have the positron beam. So my student brought the EM calorimeter prototype together with their MCP and did some preliminary tests at the beginning of this year. And very recently, they are still doing the data analysis. We haven't finished the final analysis yet. So we use the 3 times 10 to the 4th positron per second to do such a combined analysis or measurement. Okay, all the previous things are about the fundamental science. Now, since we are building a laboratory in the local, local, so I'm just quickly show you how the gallery of the laboratory developed. So we were also one of the members in the COMET experiment. So we built a Muon beam monitor. Future, it will be also used in the MACE experiment. And the second one is we also built some cosmic ray muon muSR detector system to measure the cosmic ray muon polarization. And we also built the muography detector based on such a scintillator. And also we built some portable cosmic ray muon detector, which have the educational purposes and also the applications, multidisciplinary applications. So this is the Muon beam monitor for COMET. We published last year, and the electronics was in collaboration in the USTC electronics group. So this is the detector looks like. I just quickly go through with it due to the time constraints. So we have very good measurement of the timing structure in their Muon beam line in the COMET experiment. And we also measured the beam profile very well, and also tell the accelerator crew that how their beam looks like and whether this kind of timing structure will affect the physics data taking in the COMET. And also for the educational kit, this we brought it to we built it in the local campus laboratory. We brought it to the mountaintop. We even brought it to the airplane in the business trip. And we even put it into a tunnel, cross the river, and to check the silt, whether it has some, different thickness, and it matched our data very well. We also had this kind of mu grid for the tracking. This is the original PACE founder. We start with Monte Carlo and the module test, and then customize the electronics, and then do the online monitor with the tracking possibilities. Well, eventually, this is the centimeter scale. 5 centimeter sensitivity for tracking. And then later, we upgrade it towards a new geometry, and then we reach like few millimeter and tracking resolution. So this is how it looks like. And we put it into a building and check. Eventually, we want to measure the gap between 2 buildings, but due to the mismatch, the position, the mismatch in the direction, we eventually monitor only the building itself, like this building and this building. I used to live in this building, and this the detector looks like, okay? And also due to, since we are using so many plastic scintillators, we also fabricate the scintillator by ourselves in collaboration with some material scientists. So Jian, professor in our university, and this is some of the results. So again, for the muSR, in future, definitely we will not only working on the muon science, we want to also work on the muon applications. So like muSR technologies is use the polarized muon to hit the target sample, and then to check the local, basically magnetic density or the magnetic field. So because this is the red line is the decay exponential curve, while these wiggles were caused by the local magnetic field. So we can see that the muon spin can be very sensitive to this kind of local magnetic density. That's the way how muSR spectrometer works, and it is already applied in physics, chemistry, material science, and biology. This is how we did the R&D. This is the CAD design, and this is the Monte Carlo simulation. This is the simulated data analysis and fit, and this is how we eventually build the prototype and assemble them. Finally, we can get such a detector. And one day, I also realized, since atmospheric neutrino flux still have uncertainties which can harm the neutrino oscillation physics, if we can have better measurement of the cosmic ray muon polarization, which could help with or facilitate atmospheric neutrino physics. Well, very recently, we just submitted a paper on this direction, because in the old days, people spend more time or energy in the efforts in the energy spectrum zenith distribution, but now the spin polarization should be paid more attention. And this is the result. We make a comparison with Honda, and also we try to identify the final observables. And then if we can improve the atmospheric neutrino flux understanding, we can improve the atmospheric neutrino physics analysis, like theta 23 and delta CP measurement. So this brings me to the summary. So muon physics is a hot topic. It could do the precision measurement of QED or standard model physics, or even to go search for new physics beyond standard model. And we proposed the MACE to make a breakthrough in muon physics. Significant progress has been made in the design and also Muonium target and offline software and some prototype like step detection system and reconstruction algorithm. In the local laboratory SMOOTH, we built several different detectors, including cosmic ray muon detector, muon beam monitor, and muSR prototypes. And we wish that we could use this cutting edge science to drive the technological applications. And especially after the experience accumulation in SMOOTH laboratory, we wish to get the multidisciplinary application using muSR. So welcome everybody to join MACE and looking forward to fruitful result. These are some collaborators in the MACE working group. It's about 50 people. So that's all from me. Thank you.
Yeah, so thank you very much, Jian, for a very interesting talk. So we have some time for questions, but we have to keep in mind that Jian has to leave at 12 sharp. So you can just speak up or raise your hand to ask questions. Yeah, Yevgeny?
Oh, hello. Thank you very much for the very nice talk. I'm Evgeny Stanik from the University of Sydney. I was just wondering, do you know if there are plans in China to do Muonium spectroscopy experiments at these same muon beam facilities?
You mean the Muonium spectrometer or Muonium hyperfine structure experiment, right?
So for example, hyperfine structure or 1S, 2S measurements. So spectroscopy, precision spectroscopy.
Yeah. So, well, we organize domestic workshops every year. So people are still asking, especially accelerator physicists, but I think not so many local people are really working on this. So it's new. I think if you are interested, you can propose something, and we can invite you to give the talk and then convince more experimentalists and accelerator physicists. Yeah.
Thank you, Raj.
Thank you.
Yeah, Bruce?
Hi, so thank you for the talk. I don't think you mentioned much about the data acquisition for the experiment and how it's managed, because it's a somewhat unusual arrangement. I mean, it's being driven by a bright beam. You're looking for very rare events.
Right.
How is this done?
Okay, so thanks for the nice question. And this is a very sharp question, honestly. So that's why, we have no beam yet, but our R&D has started. So that's why I built various cosmic ray muon detectors. Okay, we are also developing the data acquisition system for our muon detector. and for the COMET experiment as well. So like this electronics board was also developed together with electronics engineers. So we are working on this direction. So the conceptual design is mostly, done by the simulation, optimization, and so on, and the geometry, and also different detection system. But the data acquisition in simulation, we are now gently plug it in. And for the prototype tests, I would say we are using the small or cosmic ray muon detector to ramp up our R&D work. So, but yeah, you're right. Definitely we should spend more time and invite more experts to work on that. Thanks.
Just another question while I have the line. Why is aerogel optimal for the target? You didn't explain.
You mean the aerogel powder or silica aerogel? Why we use it, right?
Why using aerogel for the target? Is it some sweet spot for the density, or is it a?
Yes, it's a low density, and
I understand about aerogel. I just don't understand why it's optimal.
Well, okay, so in the old days, in 1999, those guys used the silica powder. Okay, but it's also not very easy, and also the efficiency is not high. And as we tried the silica aerogel, the protection efficiency, this is a full process. Basically, mu plus capture the electron, and then it starts with epithermal scattering, and then do the random work towards the vacuum. Okay, so you can see that we use the laser beam to generate this kind of perforated holes in such a low density silica aerogel. It increased the efficiency immediately. Okay, so this is why there are holes to let more muonium do the random work into the vacuum.
Okay.
So I hope I answered your question.
I'm going to need to look at the original, but thank you.
Yeah.
Okay. Any final question? Because I'm very off the time. Jian has to leave.
Okay. So thanks for your nice invitation.
Yeah,
I'm happy to finish such a seminar and keep in contact. You can also send a question to me by email. Okay.
Yeah.